Let's look at an example of calculating the exact shear distribution, and we'll go ahead and do it for the rectangular cross-section. So that was the case that we were looking at before. And so we'll assume a cross-section of dimensions h by b, so height h with b, and we'll go ahead and try and calculate the shear stress distribution for a given shear force on the cross-section. And so this will come out parabolic, as I mentioned before. So recall, so the expression for the shear stress on this cross-section is going to be the shear force V at whatever x value that we're looking at times Q at some value, so the vertical value, divided by IB. And if I write out the expression for Q, that's the first moment of the area, so that's the integral of y dA over the area above some location y1. So y1 is some value here, and a y1 is the area above y1. So that's the setup here. And so we really just have to calculate that one value there, that integral for Q. So if I write that out a little bit more carefully, so the integral over the little shaded green area goes from minus b over 2 to b over 2 with respect to z, and with respect to y goes from y1 to h over 2. And this will then allow me to calculate the first moment of that area. So the integral with respect to z is just b, and then the integral with respect to y is y squared over 2, evaluated at the limits y1 and h over 2. So if I plug that all in, I get v at the given cross-section divided by the moment of inertia I, 1/2 h over 2 squared minus y1 squared. And this gives me the stress at any location x and y1 in the thing. If I make a plot of that shear stress, it will be a parabola, and it's going to be 0 at the top and the bottom faces of the beam, and it takes on its maximum value right in the center, and the maximum value is 3/2 v over a, so it's 50% larger than the average value that you calculated just by dividing the shear force by the area. And that's one of the important reasons for doing this more careful calculation of what the shear forces in beams are. We can also kind of look at what the stress state looks like overall. If I draw in the stress state due to the bending stresses on the cross-section, then I have a linear variation, and so we can kind of plot at different locations. So at the red point, which is at the top of the beam there, I only have bending stresses, so they're just normal stresses in the x direction. If I look at the orange point, which is right in the center of the beam, then the bending stresses are 0 there, but I have shear stresses. So the shear stresses are maximum at the center there, the neutral axis, and the bending stresses are maximum at the top and bottom faces of the beam, but there's no shear there. If I look at an intermediate point, say the green point, then I have both bending stresses and shear stresses, and so they superpose the values from the shear and the values from the bending. And if I look at, say, the blue point, which is below the neutral axis, I have the same situation. The shears look the same as the green point, but the bending stresses are now going in the opposite direction because I have compression down below. So I've assumed that the bending moment is acting in the direction shown, so basically about the negative z-axis for my drawing here.